I'm very glad to be present here and present our scientific research on a topic, the concept of creation sensory feedback for lower limb prosthesis using IoT technologies. Classical mechanical prosthesis does not provide adequate sensory feedback, which limits the user's adaptation, reduces confidence in walking, makes it difficult to maintain balance during movements. The implementation of sensory feedback in lower limb prosthesis involves registering mechanical loads, processing the corresponding signals, and transmitting tactile information back to the user. This requires the creation of a comprehensive system that will include appropriate sensors, amplifier modules, actuators, as well as appropriate software. Here you can see the implemented sensory feedback systems in some popular lower limb prostheses. Our research uses solutions that combine sensors, energy-efficient amplifiers, as well as compact and comfortable for wearer designs that can be integrated into shoes or the prosthesis itself. In this case, it is proposed to place the sensor in a special insole that will be inserted into the shoes that the user will use. A piezoelectric transducer was used as a sensor in this research. The signal from a sensor is proposed to be amplified and ensure real-time operation immediately fit to the actuator. As an actuator, it is proposed to use miniature electromechanical transducers that will form small vibrations that the user will perceive with skin mechanoreceptors. At the same time, such actuators can be placed either in a special cuff, which will be placed on the free area of stump skin, for example, or inside the prosthesis stump receiving sleeve. The research analyzes several types of piezoelectric transducers, and we selected in our research transducer KP2724 type. Figure 4 shows the signal waveforms from such a assembled sensor, which were recorded with slight pressures on its surface. A low-frequency Class D amplifier on a PAM8403 chip was used to amplify the sensor signal, and Chico N7 vibromotor was used as an actuator. A mock-up of the insole was used to evaluate the performance of a designed system. Using the SolidWorks program in its lower part near the heel area, here was made a place for assembled sensor. The insole itself was made using a 3D printing from TPU material, and its final appearance is shown in these figures. Figure 9 shows the appearance of a sensor, amplifier, and vibration motor connected together with the same impact on the sensor. The vibration motor starts to work and create vibrations, which in the future will be perceived by the user's skin through mechanoreceptors. Thus, the system structure shown in Figure 10 was implemented as a prototype. All components, sensor, amplifier, and vibration motor were integrated and tested as a single system. The results of experimental testing confirmed the correctness of the choice of technical solutions, sufficient sensitivity to dynamic loads, and functionality of a system in conditions close to real operation. But such a system is quite primitive and represents a direct amplification channel without additional feedback. And it also does not provide for additional settings for the operation of actuators, except for the vibration force of the vibromotors. This limits its functionality and reduces stability. Therefore, the concept of IoT and machine learning was used. The structure of such a system is shown in this slide. Additionally, includes the amplifier module, after which a Bluetooth module is installed to implement a wireless data exchange channel with a smartphone. The smartphone is intended for the user to perform basic settings of a sensory feedback system and their subsequent storage in a controller, which after setup will automatically generate the corresponding actuator control signals during the constant use of the prosthesis without connection with smartphone. It is planned to develop a specialized mobile application for this purpose, with the ability to set the basic output parameters by the users, which are described in more details in the papers. Having signals from a sensor when the user moves over different types of surfaces, based on machine learning methods, the application will form groups of informative signal scenes for each type of surface and transmit them via the reverse Bluetooth channel to the controller, which will be store them. In the future, when moving over different surfaces, the controller will be able to automatically identify this type of surface and adjust the parameters of the actuator control signal. This will actually provide the principle of sensory feedback without the need for constant visual control of the movements being performed. Thank you for your attention.